at least one method of how the ancient Egyptians, or very ancient Egyptians, may have used in designing the Great Pyramid. That is the largest pyramid on the Giza Plateau in Egypt, known as Khufu's pyramid or Cheops. So we're concentrating on that one because that incorporates all this beautiful geometry. So basically we start out with just a single point. We're going to be looking at it just from the side, not in plan view, from the side. We'll draw a horizon line through here. Okay, now at this point there's a singularity there. We'll take our compass. You can set the compass at any radius here because we're working in ratios and not increments of measurement. So that's just a random setting that suits the size of the picture that I'm going to draw. So we'll draw a circle out from that singularity, or that singular point. If we were talking in terms of the tree of life, these actions here are some of the first actions that we'd take. But we're not going to talk about the tree of life too much today. What we want to do is, from this point on, we want to be able to draw a square over the top of this circle that is equal to the circumference and the surface area. So let's at this point let's call that an original radius and give that a value of 1 in this circumstance. So the next we want to draw a couple of opposing Vesica Pisces over this drawing, and so the way we do that is we use a radius that has a value of 2, so that's not difficult, and we just take the diameter of this circle. If I can be so careful here. Alright, so that's, and we just take the arc through above and below the circle. In this drawing we don't want to continue that circle through. It'll just confuse the drawing. It probably look nice on a big canvas on the wall or something. You'll find this is going to be quite a pleasing design anyway. So what we've done there, we've created our first Vesica Pisces at this drawing. Because geometry is such a beautiful sort of fundamental thing, what we can do now, which we'll need as a construction line as well, is draw a line through the axis, through the singularity and these 3 points. So nice and carefully draw a line through there. There we go. So, and again, because you know, sacred geometry, geometry is such a beautiful, simplistic thing that exists. What we've got there is we've created 4 perfect right angles simply by using a pencil, a straight edge and a compass. So now when I said we wanted to draw opposing vesicas for that original vesica, we use this axis here, this horizon line. Now we're going to take the compass point and place it on the vertical line, and we're going to meet at the horizon line there. So there we go, and then we'll just on the opposing side here we'll just create another arc through, and I'll just take the arc a little bit past, just so that it's accentuated slightly, keep our design a little bit tidy. Alright, so what we've got now is we've got four points in those vesicas that are intersecting. We'll just highlight them. There's one there, one here, one there, and one here. So alright, now what we want to do is just connect those four points up with your straight edge. So try and do this as neatly and as you can, if you're going to be doing this. And the ink in this pen tends to bleed across the page a bit, but I quite like the white against the black. That's why I opted for this. I'd probably get a much tidier result if I just used whiteboard with a black pen or whatever. Just bring that down a little bit lower. This is one of the hardest things, is being accurate when you're drawing these things. Because just 1 millimetre out, you can really mess your drawing up as you move along, and you can start to wonder if the geometry actually works. When it does, but it's usually because of the discrepancies in where you've placed your compass or the thickness of your drawing instruments and things like that. Anyway, back to this. What we got here is what I mentioned earlier, was the squaring the circle by using these opposing vesicas and finding these 4 points for the exterior points for our square. There's I won't be able to do any equations here to prove it, but if you take my word for it, the area of this square here is exactly the same as the area of our original circle. That's pretty exciting stuff. To me it is. So I'll just take the time right now to draw another circle in place that we can talk about a little bit more as we move along, and that's a very small one, using this radius here I have to be very careful what I'm doing. I feel this is about to slip. I want to get to this point in the video and... Alright, well, we got to that point. Okay, now we want to draw a third circle within this drawing, and we want to get that circle inside that square, so that's not difficult. Again, all we need to do is take that as our radius here. Squeeze it down a little bit. I don't know about this kid's compass here. Alright, so let's use that as the radius for our next circle. Now, I hope you're not getting confused with too many lines here, but I'd have to agree with myself that that's a pretty beautiful piece of geometry to look at, and it's not by any means a bunch of circles and lines and arcs that are just randomly put together. Because what we're going to find next is something quite a revelation as far as the Great Pyramid of Giza goes. I'm just going to draw 2 more lines in here, and that's from this point on the inner circle to the centre of this top circle. And the relevance of these 2 circles is about to come quite clear. We'll try and punch a few numbers on the page. Whether I do it successfully or not is another matter. Alright, well, what you can see there is a triangle. We've created a triangle. This triangle that we're looking at in elevation here is the exact same proportions as the Great Pyramid on the Giza Plateau. And now, when I say that, let's say, for example, if I took this line and took that line through to this point instead, we would have a completely different set of mathematics, and it would not fit all of this perfect geometry. So it would probably have its own geometry, that it wouldn't work with all of these encompassing constants that we'll be able to see. So what we end up with here is something quite beautiful. This inner circle, we can describe this as the Earth. The ratio between this circle and that circle is the exact ratio between the Earth and the Moon. What it boils down to basically is that it's as 11 to 3. What we have at 11 and 3, the ratio works out to 3.6. which isn't necessarily a relevant number to us right now, but we'll see that it definitely becomes a relevant number. So we'll be wondering how I came to this number of 720 times 3. If we multiply that by these ratios in as far as the moon goes, the diameter of the Earth, 7,920 divided by 11 equals 720 times 3 equals 2,160, which is, these are both the dimensions of the moon and the Earth. And did I describe this triangle here, which is the 3, 4, 5 triangle? It's described by Pythagoras. So basically, the equations within this Pythagoras triangle we can transpose over here. So what we're going to do is just have a look at 3 times 4 times 5 equals 60. So let's multiply 60 by 3, and I think we get 180, and so we end up with 180. If we multiply that by 2, this sure sounds like I'm making up numbers, it sure does. That'll equal 360. Then if we double that again, times 2, we end up with 720. Oh, this is interesting because it's all pertained within this drawing, so it's not something I just plucked out of the air here. These are multiples, and what we needed to bring it down to was a multiple that would be able to describe the dimensions of this pyramid in relation to the Earth and the Moon on the ground in practical terms for the Egyptians to build it. So basically it's 720 times the width of this will equal the diameter of the Earth. Alright, so there it is. There's some pretty amazing stuff in that, and we could get into pi, we could get into phi, but we won't. I just wanted to describe this to you, and I've got some little cutouts when to show you, just describe it a little differently. I'll highlight it a bit. So if we bring in this little cutout and overlay the Earth, and we'll call that the Earth. We'll bring in, notice the blue, this is blue, the blue planet. We'll have this as a blood moon because it looks like a full moon. And then the final little piece we're going to put on top is we're going to put the pyramid of the Great Pyramid in there, and there you have it. And I think I'll leave you with that today. There are some other ways drawing this. This is by no means the only way. I think you'll find the mathematics all works out exactly the same. And there's we'll probably in another video I might show you some more really elegant geometry using the Vesica Pisces to describe the pyramid at its three-dimensional view. So there you go. Have a lovely evening, and see you on my next video, whatever that is. Might catch a snake or something and put that on video. See you later, guys. Alright, well, just thinking about maybe another video, I'd probably like to show you a very simple but very elegant piece of geometry using the Vesica Pisces, which you'll see here, and repeated here, here and here, that describes the pyramid of Khufu, the Great Pyramid, in a three-dimensional view. That's to say, looking at the pyramid from one of the corners, like this. So that this would be two sides of the pyramid. So if I just try and show you, that's pretty simple to understand, I guess. But here's a bit of a cutout that I can overlay on there. So these this is just the beauty of the Great Pyramid. It fits into all of this stunning geometry that's so simple that virtually originates with the tree of life and the singularity. Anyway, it just we'll have a look at why we're looking at it from the corner. So it's basically looking at it from this view, whereas the previous geometry that I've been showing you describes just one face of the pyramid. They're all slightly different, but we probably don't need to go into that. The differences are minimal. So anyway, in the next video, don't know when, I'll show you how to draw this gorgeous little picture here. Let's put that back. Groovy.